Okay, welcome to part 2 of sigma notation. Hopefully I didn't lose anyone in the first half, but if you are getting a bit frustrated with it, that's understandable. I think a lot of people really struggle with this the first time they look at it. For some of the application, you might be wondering why if I look at a series like the one below here, 3, 6, 11, 18, 27, you might be saying to yourself, I already know the sum of a series. I already know some equations. Why can't I just apply those equations? These are two equations that might come to your mind. The first one is the sum of a geometric series, and the second one is the sum of an arithmetic series. Now the problem that you get to is trying to use the first one is that what number do you actually use when you're trying to find out r? Notice that you seem to multiply the first term by 2 to get to 6, but that doesn't happen from the second to third. So it's clearly not a geometric series. So you might look at something like an arithmetic series. It looks like you add 3 in order to get to 6, but then you add 5. So it appears that it's not an arithmetic series either. So the problem here is that we have a question or a series in which we don't have an arithmetic or geometric necessarily. So when we write this, we can go right back to our sigma notation, which is sigma, and then we can say r is the first term all the way up until the fifth term, which we know goes from 3 all the way to 27. Now the big question here is what is the relationship between what the first term is and r actually equaling 1, or what the second term is and r actually equaling 2. So as you go through, you might see, yeah, I can see a pattern. It appears that if I multiply each term number, that is, each term number by 3, so if I multiply r by 3, I seem to get the next number. Is that completely true? Well, it looks like as soon as we get to 11 that it's no longer true. In fact, when we look at 11, 3 times the third term is 9, but we're expecting 11, so this isn't necessarily the case. You have to make sure that you stop and really consider all of your numbers in your series. So what other possibility is there? As you sit here and think about it for a while, it is possible that coming up with the relationship will take you a while. To make it a bit shorter, it appears that the nth term, or the number n, is related by squaring, or in this case we're talking about r, squaring r, and then doing what to it? Looks like we add 2. So see if that, stop the video and see if that works for all of your numbers. So let's look at a question that might come up in a very simple setting. So here the question is find the sum of this series. She says these series, but we'll correct that to this series. We have the restrictions are it starts at 1 and finishes at the fifth term, and the relationship between the term number and the term itself is the term number, or r, plus 3. Which means when you think about it, the very first term would be, if I just plug in the number 1 for r, the very first term you would get is 4. You can plug in the rest of the term numbers and you would find that the second term is 5, the third term is 6, 7, and then 8. So what we're simply doing is just adding up all the terms, which in this case is 30. But what do you do when the number is very large? So in this particular case, we start at the first term, but we go right up to the 70th term. Now, do I really want to find out what each term is and then add them all up? No, that obviously doesn't make sense. But we have found out that the first 5 terms are 4, 5, 6, 7, 8. Using a bit of intuition, you could say this is an arithmetic series where the difference is just 1. Few other pieces of information we could find just simply using an arithmetic equation, and we find that the 70th term is 73. Using our equation for the sum of an arithmetic series, we have 2,695. A lot of numbers added up, but much easier using the formula now that we know it's arithmetic.